We're going to start a review today, which probably won't finish. So I picked out 60 questions out of this document. Probably going to take more than just an hour and a few minutes to get through it. So we'll finish it up on Tuesday. All right. Any questions or problems up to this point? Okay. Got everybody accounted for here. All right. So let's start with number 2. Which form of electromagnetic radiation has the longest wavelength? You can either memorize the spectrum, say, I know which end is the longest and which end is the shortest, and where everything goes. The way I tend to do it is I say, which one with the longest wavelength, which one has the lowest energy? I know gamma ray is not it. I know X-ray is not it. They're pretty high energy. So what do we have left? We got microwaves, radio waves, infrared. Infrared is close to red, so it's probably not going to be out of those 3. So it's a toss-up between radio and microwaves. So which one comes first as you're heading toward the longest? The microwaves. So the longest will be radio waves. Which of the following frequencies corresponds to light with the longest wavelength? That relates this formula, wavelength times frequency. We know that they're inversely related. So the frequency that relates to the longest wavelength, if this is the longest, let's see. Words mixed up. This one goes down, this one goes up. So short wavelength means high frequency. Long wavelength means low frequency. Okay. So we look for the lowest frequency. I would go to the powers of 10 first. Say, do we have any that are the same powers of 10? No. So all we have to do now is just find the one with the smallest power of 10, which looks like it's 10 to the 5th, the B. And you don't even have to stop at the coefficient. Okay. It's supposed to erase better. We'll put the formulas over there that we've used already, so I don't have to remember or look them up. All right, how about 6? A line in the spectrum of atomic mercury has a wavelength of 254 nanometers. All right, so one of the wavelengths of mercury is 254 nanometers. That's what we're given. When mercury emits a photon of light at this wavelength, the frequency of this light is. So it's going to emit a photon with that wavelength, and we just need to know the frequency. So we know the wavelength, we need to know the frequency. Right. So if we solve this equation for frequency, that looks too much like gamma. There we go. That would be C divided by lambda. Okay. So this would be what's C? Well, it's in your useful information, but it's 2.9979 times 10 to the 8th meters per second. That also means that this has to be in meters. So if you're using your calculator, really all you have to do is say, what does that mean? 254 times 10 to the minus 9th meters. You don't even have to put it in scientific notation to plug it in your calculator. You say 254 exponent minus 9. And that goes right here. Okay. And just to keep myself in practice. And knowing we're not going to finish today anyhow. 2.9979 exponent 8. And then divided by 254 exponent minus 9. And I get 1.18 times 10 to the 15th. What? Frequency, reciprocal seconds, or hertz. It's given in reciprocal seconds, so that should be C. Okay. I'm gonna have to get another can of WD-40. That furniture polish doesn't work as well. There we go. Number 8. Green light can have a wavelength of 543 nanometers. Now, what does that statement mean? Can have a wavelength. Our eyes perceive different colors, and they're not that discriminating. Some people more than others between shades of colors. So if we say green light, we're not specifying it's I don't know, forest green or Irish green or some other type of green. We're just saying it can have 543 nanometers. It could be a range, but we're focused on that particular wavelength. The energy of the photon of this light is, all right. Now we're talking about let's go blank. Who gave us that formula? Not Niels Bohr. It was Planck. Got it. Max Planck. The Planck equation. Well, one of his equations. Did I spell that right? Or has he got a C in that name? Yeah. So we need Planck's constant times the frequency. That's not frequency. But we can solve for frequency right here and say instead of that, we'll have Planck's constant times C over lambda. Now we can plug the numbers in. Planck's constant is 6. I have to look it up. 6.626 minus 34. 6.626 minus 34 joules seconds. And then, of course, the speed of light. Into the 8 meters per second. And then the wavelength in meters. 543 times 10 to the minus 9 meters. Meters are going to cancel. This is in the numerator, that's in the denominator. Those cancel. Leave us with joules. We're good. So, I mean, practice. Okay, there's Planck's constant. And then there's the speed of light. And then there's the wavelength. There we go. And I should get energy of 3.66 times 10 to the minus 19 joules. Okay. All right. Scroll. 11. How many of the following are incorrect? All right. So let's see, we have four. Yeah. How about the first one? The importance of equation E equals mc squared is that energy has mass. Yeah. Energy in the form of light. Right. That's true. Electromagnetic radiation can be thought of as a stream of particles called photons. That's the particle nature of light. Yeah. Electromagnetic radiation exhibits wave properties. It does that too. Right. And energy can only occur in discrete units called quantum. Okay, energy. We know light can. What other forms of energy? Well, we only know about energy in terms of light. That's could be a little misleading. Probably should be more specific with electromagnetic energy, yes, can only occur in discrete units called quanta. And the interaction of electrons in an atom with light is quantized also. So if that's what we mean, then that's true. And I think that's what we mean because the answer is E. It would be better worded if we substituted rather than energy to say something like light or electron transitions, something like that. They're definitely quantized. Okay, let's see, 12, 13, 14 are based upon, and 15 are based upon this chart and statement right here. Following 4 questions refer to this chart. So 12, 13, 14. All right, what are we looking at? Emission spectrum of hydrogen, photoelectric effect. All right, the question is, electrons have wave properties. Which of these support that conclusion? Oh, okay. What's the evidence for electrons have wave properties? Emission spectrum of hydrogen? I don't think so. Photoelectric effect? Well, that has nothing to do with waves. That's particle nature. Scattering of alpha particles by metal foil? Well, diffraction? Yes. Electrons. We didn't talk about this much in class. Electrons and diffraction. Where do we have evidence of electrons and diffraction? Remember what diffraction is? It's a wave property that whenever a wave encounters an edge or an opening, a slit or something like that, that serves as a point source for the new wave. Right? So it can happen at an edge, like you had an edge here, and your wave's coming along like that, like that, like that. Instead of just blocking it here and the wave going like that, it actually starts here and propagates like that. That's diffraction. Now, where do we see diffraction in electrons? The best example of that is the electron microscope. It uses the wave nature of electrons because the larger the mass, the smaller its wavelength. Like I have a wavelength, but it's extremely, no. Hold on a second. Relationship between wavelength and mass. Okay, I'm getting into something now. We're going to have a question about that in a little bit, de Broglie's equation. But we use electrons in this microscope because they are able to discern smaller
distances between features. And that must mean because the electron has a smaller wavelength. Because the wavelength limits it's called the diffraction limit for a microscope. You can only magnify, let's see, has anybody taken microscopy in here? No. Used a microscope? Okay. So you know that as you get down higher magnification, say you're 100x objective, right? Times what? Your eyepiece is usually 10, isn't it? So that's 1,000 times magnification. Things get kind of fuzzy when you're looking at them under that one. And that's because you're reaching the limit of light diffraction and the particles in the slide. If you use electrons, you can go down further, like 20,000, 30,000, some are even down to 100,000 times magnification. But it all has to do with the wave nature of electrons. So D gives us that answer. How about 13? Electromagnetic radiation has wave characteristics. Well, for the same reason, electromagnetic radiation exhibits wave properties as diffraction. In other words, set up a slit and you don't get the light waves passing through the slit, right? You don't get your detectors over here. You don't get just a bright spot there. Right? You get a graded, weaker signal as you move away from that spot. And that's because that's served as a point source. And it's strongest in the center where the beam is concentrated. And then as you move further away, the distance here is greater than it is here. So it gets weaker, the signal. So this one's also deep diffraction. How about 14? Electrons and atoms have quantized energies. How do we know that? We know that because of the emission spectrum of hydrogen. We only have 4 visible wavelengths in the emission spectrum of hydrogen. Now, there are other wavelengths on the infrared end, and there are wavelengths on the ultraviolet end. And they're used for different purposes. But that's confirmation of this property, quantized energies of electrons. And then the last one, spacing between atoms in a crystal is on the same order as the de Broglie wavelength of accelerated electrons. Okay, we haven't talked about de Broglies yet, but de Broglie relates the, well, actually, not just the mass, but the velocity of any particle to its wavelength. I think that goes back to its kinetic energy. Let's cut it off there. We don't need to go any more depth. We're going to get back to de Broglie. And in fact, it may be in the second semester. Thanks when we use it more. We talk about actual spacings in crystals. So we'll get back to it later. But that is also evidenced by diffraction. Right? So this one's also B. Okay. Moving on. (16) The 4 lines observed in the visible spectrum of hydrogen tell us that. I think this is like, you ever taken those personality tests of psychology, any type of psychology test? You start answering the questions and you get down to one down here and say, wait a minute, didn't they ask that one already? What they do is they ask the question in a different way, just to confirm that your answer above is honest. That's what they're trying to do. They're trying to weed out the aberrant flashes of people's minds. It might give an answer this way, that way, and that way, that way. And they take that into account statistically when they assess your personality or whatever the test is supposed to be doing. But that's what we're getting here. We're looking at 16. These 4 lines tell us that only certain energies are allowed for electrons in a hydrogen atom. In other words, the movement of electrons is quantized. It moves in discrete jumps from one orbital to another. And that's evidence for it there, that 16. 17. For which of the following transitions does light emitted have the longest wavelength? Now, here's where that energy analogy I gave you at the very beginning is most useful, because the longest wavelength is going to be the lowest energy. And the lowest energy transition for an electron is the one with the shortest distance between energy levels. All right, so which one is the shortest distance? Well, we know 2 to 1 is a pretty big jump. 3 to 2 is a lesser jump. 4 to 1 is a huge jump, and 4 to 2 is just a little bit smaller than that. The shortest jump is between 2 outer orbitals. 4 and 3 would be the smallest jump, give you the longest wavelength. So answer to 17 is A. Okay, 18. When a hydrogen electron makes a transition from n equals 3 to n equals 1, we've got a proton. We've got 1, 2, 3. I'll go ahead and put 4 in here. So we've got 1, 2, 4. And our electron is making a jump from 3 to 1. So it's going from here down to there. Okay, and it's going to give off energy. Okay, which of the following statements is true? Energy is emitted. That's true. A is true. Excuse me. Roman numeral 1 is true. There we go. Let's see. Energy is, well, can't do both. So 2 is false. How about 3? The electron loses energy. Yes. Closer to the nucleus means lower energy. So the electron does lose energy. 1 and 3 are both true. It can't lose and gain at the same time. So 4 has to be false. 5, the electron cannot make this transition. Well, that's just stupid. It's a filler. So Roman numeral 1 and 2, 1 and 3, which would be B. B is our answer for 18. So what if I got sneaky and said, just change the wording a little bit? I actually just say electron transition from n equals 1 to n equals 3. Then it would be 2 and 4. Yeah. By the exact same amount of energy. All right. 21. We're looking for an incorrect answer. The emission spectrum of hydrogen contains a continuum of colors. Well, that one's false right off the bat. And then test taking technique. Look at all your other answers. Do you have any that says 2 of the above, none of the above, that type of stuff? No. So when you find the right answer, you can stop. All right. If you're sure that's the right answer. Because if we look at the others, they should be false. Diffraction produces both constructive and destructive interference. Oh, we talk about that. Interference, destructive and constructive interference. Or is it in your textbook? I hope. All right, here's what it means. We'll probably, maybe that comes in more detail in the second semester. But when we talk about waves interfering with one another, they do that. Right? Any type of wave will interfere with another wave.
If we have a wave that's like this, and then we have another wave that we're trying to superimpose on that wave, and it's like this, they add together. And the combination of the two gives you something like this. No, nothing like that. Like this. There we go. Like this. That's constructive interference. 100% constructive, right? These add together to give you a bigger amplitude. If we shift this over by half a wavelength and say like this, now what we get is destructive interference, and the product is that. That's the idea behind noise canceling headphones. The electronics in there work so fast, they detect an incoming wave and they generate a wave that's opposite to that one and of the same strength and opposite pattern. And that cancels out the noise coming in. So you don't hear anything outside if they're well made. Right? I've got some noise canceling earbuds that don't work too well, but they were cheap. They're like $15. If you buy the $100 or $200 ones, they probably work a lot better for noise canceling. But I've heard of people, when they first came out, these noise canceling headphones, they didn't even hook them up to an external source. That's all they did. They just canceled the noise. So people would buy them and wear them on airplanes to cancel out the noise. Okay, enough of that. 22. And that's the idea behind multiplexing. When you send a signal, electronic signal, electromagnetic signal over like these microwave transmitters, how do they get all that information in there? Well, they superimpose another signal on it. That's the AM, FM, they all work the same. You have a carrier wave, and then you have the superimposed wave on it. And at the other end, you have the carrier wave that you tune in that works in opposite amplitude destructively, and it destroys the big wave and leaves the information behind, and that's what comes out to your speakers. 22. In which of the following statements best describes the Heisenberg uncertainty principle? I don't know if I can remember this one. That position, that momentum, which is mass times velocity, right? Mass doesn't change, so we have a difference in velocity, has to be greater than or equal to Planck's constant over 4 pi, I believe. Is that right? Let's look it up to be sure. See if I got it right. Oh, did I put it in here? Good. But we're not going to use it for any calculations. Maybe that's why I didn't put it in. I think that's right. So that's the mathematical reduction expression. I mean, they've got more complex versions. But what does it actually mean in practical terms? It means that you can't know both with any degree of accuracy. You can't know both where a small particle is and how fast it's moving at the same time. You can determine one of them fairly accurately, but if you do, the other one is undiscernible. So it's impossible to accurately know how both the exact location and the momentum of a particle. That's what this says, right? C.
Right. Okay, not doing too bad. Ooh, electronic structures, 25. Okay, let's see how good we are at this. How many F orbitals have the value n equals 3? All right, so we have, let's put up our quantum numbers. N, L, M sub L, and M sub S. Okay. This is energy and size, right? This is shape. This is orientation. And this is spin. Okay. So, and this is often called a shell. This is a subshell. This is an orbital. Okay, so we're talking about orbitals. How many F orbitals have the number value n equals 3? If we say n equals 3, then what can we have here? We can have a 0, a 1, or 2, an S, P, D. There are no F's for n equals 3. That's why the answer is 0. Okay. You got to get up to 4 before you can have an F. All right, so that takes care of 25. That was a trick question. 26. 26 says, how many F orbitals have n equals 6? Okay, now we're talking. If n equals 6, then we can have 0, 1, 2, 3, 4, and 5. So there's our F. Okay. And that's all we can have for F's. Just that one right there. Even though this is 6 F orbitals. So how many can we have here under F? Well, if F is 3, we can have -3, -2, -1, 0, +1, +2, +3. Right? How many is that? 7? Yeah. You can have 7 orbitals for any F subshell. All right. Let's see, 27. We'll leave that there for now. Might come in handy. If n equals 2, how many orbitals are possible? Okay, now we're going to total up all the possible orbitals if n equals 2. All right, so if n equals 2, how about L? L can be 0 and 1. Okay, about M sub L. Well, for this one, you can only have 0. For this one, you can have -1, 0, +1. So that's 1, 2, 3, 4 orbitals, right? Or n equal 2. That's what it said. How many orbitals are possible? Just 4 for n equals 2. Let's see, if n equals 2, we're going to be right here, correct? So this takes care of the 0, well, M sub L, 0 from L equals 0. And then this takes care of -1, 0, +1. Okay, so we got our answer from the periodic table too. 27, 28. Let's leave that there. 28 over here. Okay, 28 says a given set of p orbitals consists of blank. Actually, it should say p subshells. Right, that's misworded. Rather than p orbitals, it should be, let's see, I don't think I can edit this easily, so I'm just going to say it would be better for set of p. No, that's right. P is the subshell, and it's asking us p orbitals, which under p,
So P would be what? This is S, this is P. Okay, there's P. So for a given set of P orbitals, consists of how many suborbitals? Or how many orbitals in that subshell is 3? Right? These 3 right here. Is that twisting anybody's head around yet? Or you do your head twisting at home? That's good. This takes lots of practice to get comfortable with it.
29.
All right.
So which of the following is an incorrect designation for an atomic orbital? Okay.
Let's do these. A, B, C, D, E. So if we say 1S, 3D, 1P, 4F, and 6S.
Everybody's got an s orbital. Right? N equals 1, N equals 2, 3, 4, 5, 6, doesn't matter. They've all got s orbitals.
So this one's okay, this one's okay.
Okay. We just did a 4F.
We know that one's okay. How about a 3D? Well, if 3, how many of, if 3 is N, then how many L's can it have? It can have 0, 1, and 2. S, P, D. That's good. Okay. Process of elimination. Because this one can only have 0. That's an S.
There are no P's in the first period.
Okay. So C is wrong.
All right. 31. A point in the wave function where the amplitude is 0 defines what? Just memorize it. If the amplitude is 0 in a wave function, that's a node. Okay, there's no probability in that wave function of finding any electrons at that position. That's a node.
32. Write that up there. That's a node.
How many electrons in an atom can have a quantum numbers n equals 3, L equals 2?
N equals 3, L equals 2. We want to,
How many electrons are possible?
okay, N equals 3. Well, we don't have to worry about this one because we've already designated out of that N equals 3, we're only going to look at 2.
0, 1, and 2, SPD.
We're only going to look at the D's. So we need to know how many M sub L's can we get out of that one. -2, -1, 0, +1, +2. And then M sub S says +1/2, -1/2. So 2 electrons for each one of these. 2, 4, 6, 8, 10. 10 electrons
For that designation. Okay. And that's going to be where on the periodic table?
here. One of these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Right. 33. How many electrons can be described by the quantum numbers n equals 3, L equals 3, M sub L is 1?
Well, M sub L, we're saying that's 1.
So it doesn't matter how we got to this position.
M sub L is 1. That means 2 electrons. Oops, sorry. I tricked myself.
The mistake I made,
N equals 3.
can we have an L equals 3?
No.
0, 1, or 2? Right.
So the answer to this one is 0.
I went at it from the wrong direction. I just assumed that it was given to us correctly, but it wasn't. Can't have an L equals 3 with a principal quantum number of 3. You only have a 2. A trick question caught your instructor. Okay, 34? Yep, 34. What's the L quantum number for a 4s orbital? Okay.
4s. So this is N, this would be L, and S's are always 0.
0 quantum number. Okay. All right. Which of the following combinations of quantum numbers do not represent permissible solutions of the Schrodinger equation for the electron in a hydrogen atom? In other words, which combination of quantum numbers is not allowed? All right. Let's see. 9866. A, B, C, D. And E says all are allowed. Okay, that means we have to do every one of them. 9, 8, 6, 6. And then 8, 2 minus 5 plus 5. 8, 2 plus 5. And then minus 4, 2 minus 1. Minus 5. And then a half. Well, we know that these are not going to disqualify any of them because they've all got that possibility. So we have to look at the other parts. If this is N, this is L, this is M sub L, and this is M sub S. Okay, is this permissible here? Yeah. 0, 1, 2, 3, 4, 5, 6, 7, 8. That's okay. So for this one, that's all right. How about this one? M sub L minus 8, minus 7, all the way up to minus 4. That's good. So this one is okay. We're looking for ones that are not allowed. So this one is allowed. How about this one? 8, can we get a 2 out of that? 0, 1, 2? Yeah. We're good there. How about this one? M sub L is minus 2, minus 1, 0, 1, and 2. Yep, that's good. Okay, that one's okay. How about this one? 6. L from 6 is 0, 1, 2, 3, 4, 5. Nope. You can't do that one. That one's wrong. Okay, so if all are allowed and we found a bad one, that's it. See, this one should be okay. Yeah, 0 through 5 is good there. And then minus 5, minus 4, that's good. Okay, this one's all right. That means this one is no good. So, C is your answer. Technically, E would be false also, right? Because all are not allowed. That's one of those unintended consequences. Pick the best answer. Okay. Still got time. Who was the first chemist to recognize patterns in chemical properties of elements? Of the ones that we discussed. Right? Remember the triads? Who brought up the idea of triads? Dobereiner. Dobereiner was the triad king. But that's as far as he took it. He just noticed it and moved on. What until you get to Lothar Meyer and Mendeleev that you start getting the push to put things in relative position in a table of some sort. So D is the answer for 40. Over under. Sounds like a dog breed. 41. Okay. Mendeleev is given the most credit for the concept of the periodic table of elements because, remember why? Because he used the table to predict the existence of yet undiscovered elements and their physical and chemical properties. That's why he got, so that's B. All right, 44. Before the complete electronic configuration of 10. Okay, there's your answer. The complete electronic configuration. We can't abbreviate it. We can't take any shortcuts. We got to put the whole thing in for 10. Okay, so 10 has how many electrons in the neutral atom? 50. All right. So if you don't have the sequence, the energy sequence, low energy to high energy from left to right, then you can either use that diagonal, which should be printed out in the should be in your useful information. So you could use that. Or you can go to the periodic table and just follow along. We know 1s takes care of hydrogen and helium. And then you come down to the second one, 2s takes care of lithium and beryllium. And then 2p takes us all the way across to neon. And then 3s, we come down to the next one, sodium and magnesium. That's 2 more. And then we go across to 3p. We get 6 of those. Takes us to argon. Then we go down to 4s. Right? And that's potassium and calcium. Then we go across the 3ds. All the way across the 3ds. From scandium to zinc. And then we go across 4p's from gallium to krypton. And then we go back down to 5, rubidium and strontium. And then we go to 4Ds. We get 10 of those. That takes us across to cadmium. And then we have, who's left? 5P. 5P. And now we're right here. 1, 2. And that should be all 50 electrons. Let's count them up. Let's see, 4 and 6, that's 10. That's another 10, that's 20. Another 10, that's 30. There's 10. That's 40. And then that's 8, 9, 10. 10 more, that's 50. We're good. That's the whole thing. We did it using the periodic table. Oh, so that's D. You have to find the right one to give the answer. All righty, 44, 46. Statement that the lowest energy configuration for an atom is the one having the maximum number of unpaired electrons allowed by the Pauli principle in a particular set of degenerate orbitals. I didn't mention degenerate. Degenerate doesn't mean that you're talking about some moral perversion. In chemistry, degenerate means they're at the same energy level. So when we have let's see, we're at 46. For instance, if we have a p orbital, any of the p's, they'll have a p subshell, they'll have 3 orbitals in them, right? -1, 0, and +1. These are degenerate orbitals. They're all at the same level of energy. Okay. So who said that, or what rule says the lowest energy configuration for an atom is the one having the maximum number of unpaired electrons? In other words, when you start putting electrons in a p orbital, go there,
Then you put another one over here. You don't pair them up yet, like that. Then you can start pairing.
The maximum number of unpaired electrons is preferred by the Hund's rule. That's B.
And I'm sure it was named after somebody.
I don't happen to know his first name though. Or even if it was a he. Okay, 47. An element has the electron configuration. Okay, now we're doing the
Abbreviated form. I like to put the atomic number in there when we're counting things up. So that's 36. There we go.
and then beyond that, we're going to 5, 4, and 5 with 2 on the end.
5, 4, 5 with 2 here. So that's 10 and that's 2.
So, which region of the periodic table are we located? Well, this is 5p, so we know it's going to be on the right-hand side. But on the right-hand side, we've got that diagonal, so we're not really sure if it's a metal or a non-metal yet. We have to say, where do we find 5p? All right, we come down to 5, period 5, and then we come over 2. Because there are 2 electrons in that p orbital, back at 10.
So this is 10. And what is 10? 10 is a metal.
Right? So let's see. Now, if you have an answer like that, it's say germanium. Germanium is a metalloid. It's a metal, but it's also a metalloid. If there's a metalloid in there as an answer, give that one. If there's no metalloid in there, but there's metal, give that one. Pick the best answer. All right. 48, an element with the electronic configuration.
And now we've got xenon,
Which is 54. And beyond xenon, we're going to 6, 4, 5, 5d7.
F 6, S2, 4, F
14. Yeah, 14.
5,
S. No, 5d. Excuse me, 5d.
7. There we go.
So xenon would be here. And then 6s would be here. And then when we get to lanthanum, we're going from 6 to 4 because these are ratcheted down by 2 rather than 1s for the Ds. Like we have 4s here, then we have 3D here. This is 6s, and then we go down to the lanthanides, which are all the Fs, but they're 4 from 6. So you have to subtract 2. And then you go across these 14. Then you come back to, we get across to here, D7. Right? 5, 6. Is that platinum? Let's add them up. 54, 56, 77. No, it's iridium. Okay, so this must have okay. This one has 5d1. And then these are your Fs. Once you get through with those, you can come up back up to 5d, 1, 2, 3, 4, 5, 6, 7. Now you're at iridium. So iridium would be a transition element. Okay. Now I went the long way around the barn. Really, to find out what you're looking for, just add up the number of electrons and find out what the atomic number is. And that makes it a lot simpler. All right, 49. All alkaline earths have the following number of valence electrons. Valence electrons. The total number of electrons at the highest principal quantum number, the highest energy level. N equals what? So alkaline earths are here in the second column. Right? They're all s orbitals. So they have 1, 2. They're all s orbitals at that quantum number. They only have 2 electrons. Okay. That's all the valence electrons they have. That's why we memorized early on +1, +2, +3, -1, -2, -3 flip-flops. And that's where that comes from. Let's see, 50. Titanium. So titanium is 22 atomic number. That means 22 electrons. It has how many electrons in its d orbitals? Oh, all right. Scandium has 1. Titanium has 2. Has 2 d electrons. That would be 3 d2. 2 electrons. Okay. In its d orbital. Germanium. It's 50. Oh, that's not one I selected. Oh, while we're there, where is germanium? It's over here, right? So how many electrons in its 4p orbital? Is that a 4p? Yeah. It's in the 4th period. We're on the p side. Germanium has 1, 2 electrons in its p orbital. How about iron? Okay. We might need it. We're going to put it in. Okay, iron has how many? Has so many electrons that are unpaired in its d orbitals. Okay. So if we're looking at d orbitals for iron, we're looking at 3d, correct? Right. So how many orbitals are in d subshell? D is 0, 1, 2, 3. This is S, P, D. D is 2. And 2 is -2, -1, 0, +1, +2 possible orbitals. Right there. Okay. So for iron, how many electrons are in that d orbital? Well, just count. 1, 2, 3, 4, 5, 6. We have 3d, 6. So we follow Hund's rule. 1, 2, 3, 4, 5, 6. Okay. So we have 1, 2, 3, 4 unpaired electrons in D, in iron. Okay. Let's see. We're going to answer the next ones using that state. So let's see what 53 is asking. Which represents the ground state for nitrogen? Okay. That one should be fairly simple. It's got 7. Now, notice that we left out the 1s. We're only including the 2s because 1s is core. 2s is valence. 2s and 2p are valence. So we would have 1s2, 2s2, 2p, 3. 3. But it also looks at orbital structure. So here we have like that, 1, 2, 3, 1, 2, 3. So we have 2 and then 3 unpaired, which would be A. Okay. Now, the next one is which represents the ground state for N minus? If we do this, what have we done? We've added an electron. Right? We had 7 neutral, now we have 8. So where does the 8th one go? Here. Okay. So now we go back up and look, which one looks like that? And it looks like E. E is your best choice for that one. Okay. How many would it take to be isoelectronic with neon? 2 more, right? We'll just do this, this. Now it looks like neon, but what's the charge now? -3. So that was 53 and 54. I didn't write 54 up there, but that's where we were active. 55. Periodic trends. Which group do all the elements have the same number of valence electrons? Oh no, we haven't got there yet. Same number of valence electrons means they're in the same column, in the same group. So all we have to do is look at A, B, C, D, E. Well, E is none of these. So A, phosphorus, sulfur, chlorine. Phosphorus, sulfur, chlorine. Are they in the same group? No, they're in the same period, not in the same group. So they won't have the same number of valence electrons. Okay. Let's that one out. Silver, cadmium, and argon. Well, that's fairly obvious, right? That's a noble gas and these aren't. Right, so that takes care of that one. Sodium, calcium, barium. All right, sodium's an alkali metal. Calcium and barium are alkaline earths. That doesn't work either. Phosphorus, arsenic, was it selenium? Yeah. Phosphorus and arsenic are together, but selenium's not. So none of them have the same number of valence electrons. Why do we even care? Whether they have the same number of valence electrons. Same number of valence electrons means they'll have similar chemical characteristics. Not exactly the same, just kissing cousins. To use Mendeleev's terminology. Oh, he probably said it in Russian. Of the following elements, which has occupied d orbitals in its ground state neutral atoms? Occupied d orbitals. Okay, let's see. A, B, C, D, and E. Okay, we got chlorine, phosphorus, silicon, calcium, and barium. Okay. This is kind of a tricky question. Which has occupied d orbitals? So as you're building your elements, you're working your way across, you don't get to d orbitals until here. So anything above this one, anything less than 21 will not have d orbitals in it. Barium is, let's see, 56. So that's got d orbitals. Calcium has 20. It's less than 21. Less than 21 Z. Right, so calcium's not. Silicon has 14. Right? It's not. Phosphorus has 15. It's not. Chlorine has 17. It's not. The only one that has occupied d orbitals is barium. Barium's way down here. Now it has occupied d orbitals it has 4 Ds and 3 Ds occupied, completely occupied. Let's see, 59. None of the following elements, which needs 3 electrons to complete its valence shell. All right. Where would those be? 3 electrons plus 3 electrons yields the octet. I bet that's what they're after. Yeah. Which ones need 3 electrons? 1, 2, 3. This group right here, the nitrogens. Nitrogen, phosphorus, arsenic, antimony. You get a little squirrely. But nitrogen, phosphorus, arsenic will definitely need 3. Okay. Which of the following needs 3? Okay. Phosphorus. Yeah, phosphorus is in there. That's D. Silicon, calcium, barium, chlorine. All right. This is the only one that's in that list. D. Let's see. How are we doing on time? Got time for one more? 62. How many questions are in this set anyway? Okay. So we're probably in the neighborhood of halfway. 62. Go ahead and knock this one out. I'd like to find a logical breakpoint. Which of the following atoms has 3 electrons in p orbitals in its valence shell? 3 electrons in the p orbitals. 3 electrons in the p orbitals. 1, 2, 3. Well, we're back to the nitrogens again. Nitrogen, phosphorus, arsenic. Oh, trick question. 3 electrons in the p orbital. It could be any one of these, right? Because these are filling p orbitals. P1, P2, P3. So it could be any one of those. And it looks like bismuth is a good candidate. Yeah. Bismuth fits. Let's see what the next one looks like, if it's a good breakpoint. All right, let's get 66. That'd be a good breakpoint. And then we'll pick it up with ionization energies and trends with 67 next Tuesday. Which of the following is the highest energy orbital for a silicon atom? Okay, silicon is 14. 1s2, 2s2, 2p6. That's 10. 3s2 and 3p. Let's see, 10, 12, 2. So which of the following is the highest energy orbital? 3p. Now these are similar energies, but the p orbitals are adjusted up just a little bit. So these are not degenerate of one another. Now the suborbitals here are degenerates. Okay, so that's where we'll pick it up. 67. Let me